There are many situations where samples are not independent. Most of the time, this occurs when the subject or experimental unit within a study or experiment does not change across samples. This can occur in situations where the data is discrete or continuous. We will focus on the two-sample case. If the data is continuous, we use a paired t-test. For nominal data, we cannot use the typical techniques. We will need to adjust for the variability added by not changing subjects across groups. We consider this situation for categorical data matched pairs. A pair is considered matched when an observation from each sample is paired with its counterpart in the other sample. The observations are usually connected by subject. These are not independent because of the pairing. Let's look at an example. In the above situation, people are polled about their opinions on the Prime Minister in England. The first poll occurs at a point in time, then 6 months later, the same people are polled again. We consider this paired because the polling results are done on the same people. The only thing that changes is time. We would like to see if there is an association between opinions 6 months apart. Let's look at the results of the study. Here is the 2x2 table of the results. Notice on the horizontal axis is the results for the second survey and on the vertical axis are the results from the first survey. Here are some details. Notice that the categories for each variable are identical. Also, the main diagonal of the table are the combinations of the variable where the results of the survey are identical for both time periods. These are the subjects whose opinions did not change over time. They composed the majority of the counts. This means that most people did not change their opinions based on whatever occurred in the 6-month period. The metric that we would like to assess in this situation is inter-rater reliability. This tells us the extent to which opinions did not change over time. At a basic level, we can just look at the percent agreement between the two time periods. Let's look at this for the British poll example. We can calculate the percent agreement by creating the ratio of the matching results and the overall total results. For the British poll example, we get a percent agreement of roughly 85%. Let's draw conclusions. 85% is a good number. Remember that this is just an estimate. Also, how do we know what percent of the agreement only occurred by chance? We will incorporate this idea of randomness into the situation by calculating a metric called Cohen's kappa. Kappa is a way to assess inter-rater reliability while accounting for the possibility of random agreement. Kappa takes on values between 0 and 1. We consider a value greater than 0.7 as a satisfactory inter-rater reliability. We calculate the value for kappa by comparing the total observed number of agreements to the total expected number of agreements. This is very similar to how we find the components for the test statistic for the chi-square test for independence. We will determine the expected counts in the same manner that we did for the chi-square test for independence. Here is the calculation for kappa. In this case, n is the overall number of observations or counts. Let's determine Cohen's kappa for the British poll example. Again, here is the table of results with column, row, and overall total counts. The calculations are in the slide. Notice that the observed counts are much larger than the expected counts. The value for kappa in this case is 0.6996. Based on the results here, we are on the threshold. The problem with this is that this is just an estimate. In order to have more confidence that our results are consistent, we need to make inference. So to make inference, we would like to compare dependent proportions. In order to do this, we first need to define P-AB as the probability of outcome for the first observation and outcome B for the second. If we let NAB count the number of such pairs, then the sample proportion becomes NAB/N. Let's look at some details. Let's assume that NAB is a sample from a multinomial n P-AB distribution. We can get Pa plus as the proportion and category for observation 1, P plus A as the corresponding proportion for observation 2. Now that we know the distributions for these, we can build the test statistic for the equal proportions test. Recall that we are looking for agreement, so our proportions of interest will be the row and column totals for the same result. In this case, we will focus on the approved result. So the totals of interest are n1 plus equals 944 and n plus 1 equals 880. The idea behind marginal homogeneity is that the marginal probabilities are the same across time. This would mean that pi 1 plus equals pi plus 1. This leads to pi 12 pi 21. So we can build the estimate based on the difference between the sample proportions. Let's look at the hypotheses. For this test, the null hypothesis is that the difference between these marginal probabilities is 0. So this basically means that proportion where the event of interest occurred for variable 1 is the same as variable 2. How do we create the test statistic? Here we will essay the walled EST. We find the test statistic based on what is in the slide. Notice that the variance is given as well. If we use an alternative estimate for the variance, we can write the test statistic on the previous page in the form given on the screen. If we square the value, we get McNemar's test. Let's look at some details. Notice that the McNemar test is only concerned with the cases classified in different categories for the two observations. Notice that the main diagonal is not used in the estimate. This is because whichever event you choose, the other common event is not involved in within the equation for the difference in the marginals, the common probability cancels out. We can use the test statistic and find a p-value, or we can create a confidence interval. The confidence interval is given in the slide. Notice that this is based on the counts. Let's go back to the poll example and create a 95% CI. Based on the interval, the rating of the prime Minster actual decreases across time. This decrease is between 2 and 6%. Also, since 0 is not in the interval, we would reject the null hypothesis. Let's see what the hypothesis test gives for results. Here, since this is a z-test, we will use the normal distribution. For alpha equals 0.05, the critical value becomes 1.96 for a two-sided test. In this case, we will reject the null since 4.16 greater than 1.96. Let's draw conclusions. Since the interval does not include 0, we reject the null, which is the same result as the hypothesis test of equal marginal proportions. We can conclude that the opinion of the 1,600 voters has dropped between 2 and 6% between the first and second surveys. Let's take a look at what SAS gives us. Here are the commands. Notice it is the same as what we do for the independent case, except we will put the agree option in the table statement and add an exact statement with mnum. Let's look at the output. You can see within the output that we get a p-value for the McNemar test. Also, we get the value for kappa and a confidence interval. Based on the results, the p-value is significant. SAS yields the same results that we got by hand, and it outputs a CI for the kappa value but not for the difference in the proportions.